Hello, good morning student. How are you? I hope all are you happy, fine and healthy at home. So, what did we discuss yesterday? Yesterday we discussed about the SN1 reaction kinetic and mechanism. With the following point we have discussed this SN1 reaction, the kinetics, proposed mechanism, transition state, attack of nucleophile and energy profile diagram and the stereochemistry. So in this way we are studying that SN1 reaction step by step. So in the previous lecture we have discussed about energy profile diagram. Energy profile diagram is what? The graph obtained by plotting the graph obtained by plotting the graph potential energy versus reaction coordinate is known as energy profile diagram. And in energy profile diagram for SN1 reaction we have got two transition state, and with the help of suitable example we have seen. So today we are going to learn, or we are going to discuss the SN1 reactions stereochemistry means racimization. That is the point. Today we are going to discuss the SN1 reaction. Stereochemistry means racimization. And the SN1 reaction, what is SN1 reaction? We already learned that one. Let us revise that one. SN1 means substitution nucleophilic unimolecular. That is known as a SN1 reaction. And it is a unimolecular reaction, and we got this unit from the study of kinetic of this reaction. Now the stereochemistry, I have stereochemistry racimization. In bracket we have written racimization. As far as the SN2 reaction is concerned, there we have written as a inversion product. Inversion product clearly indicate that there will be a nucleophilic attack from the back side. So that clearly indicate that in a SN2 reaction there is a complete inversion takes place. But here the racimization is nothing but it is a process of, or there is a mixture of enantiomers. Enantiomer, as we know, that non-superimposable mirror images of each other are known as a enantiomer, and there is a equal proportion of that we are getting. So that is called as a racimization, means it is a racemic mixture, and racemic mixture are optically inactive in nature. As we know that similar to as a meso compound also as a optically inactive, racemic mixture also are optically inactive in nature. So for stereochemistry, there for study the 5 mark question always appear in the exam. What kind of the question it is? What is SN1 reaction? Discuss the stereochemistry of SN1 reaction. So stereochemistry, if you take as a starting material in the while general reaction we are taking as a tertiary butyl bromide, hydrolysis with sodium hydroxide yield tertiary butanol, but the starting compound is achiral in nature, and achiral are optically inactive. And for to study the stereochemistry, whether we are getting racemic mixture means enantiomer. Enantiomer, as we know that everything is the same. Chemical properties as well as physical property of the enantiomer are same, only they differ in their rotation. One is rotating the plane of polarization right hand side, another rotate the plane of polarization to the left hand side, means one is a dextrorotatory, another one is a levorotatory motion. So that type of the the optical rotation they are showing, that type of the stereoisomer is known as enantiomers. So for study of stereochemistry, racimization, here we are going to take the general reaction starting with the R1-phenyl ethyl chloride is treated with the aqueous sodium hydroxide gives 75% of S1-phenyl ethyl alcohol and 25% R1-phenyl ethyl alcohol. So that the product we are getting. What I said here just now, the starting with that, what is that? We are taking here, first one is a R1-phenyl ethyl chloride treated with aqueous sodium hydroxide or hydrolyzed, or the R1-phenyl ethyl chloride hydrolyzed with, treated with or hydrolyzed with sodium hydroxide gives 75% S1-phenyl ethyl alcohol or ethyl alcohol and 25% R1-phenyl ethyl alcohol. So that is a product, or this is a general reaction we have considered here for the study of the SN1 reaction, stereochemistry of SN1 reaction we are studying. Now, most of you might be knowing the structure of R1-phenyl ethyl chloride, right? Now, R1-phenyl ethyl chloride, as we know that 1-phenyl ethyl chloride indicates there are two carbon atoms. At one position, phenyl group is present, and other end, that is chloride, is present. Let us see here. Suppose we have this Cl and I am showing this one CH-3. Methyl group, carbon atom and the chlorine atom I am shown here by normal line. It clearly indicates that these three atoms are present in the same plane. Now I am showing one of the bond by dotted line that clearly indicate that hydrogen atom goes away from the observer or it is below the plane. Now I am showing another bond which is thick that clearly indicate that the bond is above the plane, and there we can write as a pH. And as we know that pH means what? Phenyl group. pH, you can write pH, or it is a phenyl, it is pronounced as a phenyl, or we can write in short C6CH5, or you can write this one phenyl group, that is a monosubstituted like this, right? So that are the various way to represent or to show the phenyl group. I am showing here one way, that is a pH means phenyl group, benzene, right? And now this carbon atom, as we know that shown by the RT means this star indicate as a there is a one chiral carbon atom. If chiral carbon atom is present, this molecule whole becomes as a chiral in nature, and chiral molecule are optically active in nature, and the instrument used to determine, to measure the optical activity. What is the name of that instrument? Do you know? Yes. What is that? Polarimeter. Polarimeter is used to determine the optical activity of that compound. The name of this compound is a R1, because here look at only 2 carbon atoms are there. This is carbon number 1, you can call it as a carbon number 2. At one position chlorine group as well as phenyl group both are present, and therefore it is termed as a 1-phenyl ethyl chloride or 1-chloroethane, you can call it as 1-phenyl ethyl chloride. So that is the name of this compound. Now why it is R? Do you know R? By using as a sequence rule, we can give the priority number and see the rotation, whether the rotation is a dextrorotatory or the levorotatory. Look at here, this is a chlorine atom, this is carbon, here also as a carbon. Which one having highest atomic number? Chlorine is the highest atomic number, is having as atomic number is a 17, and therefore it will get the first priority. Now among these two, which one is a bigger one? Methyl group or phenyl group? Phenyl group is a bigger than the methyl group, and therefore it will get the second priority. Methyl group will get the third priority, and the fourth priority, the hydrogen atom will get the fourth priority. Now only see the 3 groups, 1, 2, 3, always start from 1, start the arrow showing from 1, 2 to 3 only, and then look at if that hydrogen atom is below the plane or above the plane, there will be no change in configuration. What type of the rotation you can see, what type of the motion you can see, there is a R, and that's why it is a R1-phenyl ethyl chloride. Understood this one? Now when there is a SN1 reaction, solvent is used here. The step number first, as we know that it is a rate determining step. Rate determining step means what? Rate determining step, it is a slow step where we can measure or we can determine the rate of reaction, how much time is required to break the bond between chiral carbon and the chlorine atom. When it breaks, it attains or it acquires this type of the transition state. Methyl group you can write here, one of the hydrogen atom you can show here, and this phenyl group you can show like this. Here is a pH. Now the intermediate is formed as a carbonium ion, and this is called as a carbonium ion, or it is termed as a carbocation. The organic species carrying positive charge, that species is known as a carbocation or the carbonium ion. Now look at when it attains, and this carbocation is a very stable in nature. Look at, there is a phenyl group. Let me show you here how it is stabilized. Look at here, suppose there is this phenyl group, I am writing this pH is like this, and there will be this one C, then CH-3, H positive charge. That is a benzylic cations are there, and these benzylic cation, as we know that, is well stabilized due to the resonance. This double bond shifted from here to here, and what do you get? You are going to get here this one, this double bond and this double bond, they are as it is. When I am shifting this double bond from here to here, there is a double bond formation CH-3. What type of the charge present on this corner point? There will be a positive charge, remember here. And next one, again this double bond shifted from here to here, so etc. And as we know that number of resonating structure goes on increasing, the stability of that molecule goes on increasing, and therefore this carbocation is a highly stable one. And if you look at this one, carbocation is a trigonal, it acquire or it attain the trigonal geometry, or it get the trigonal geometry, and bond angle of trigonal trigonal is 120 degree. If you look at as a starting compound, this is a optically active substrate and which has a chiral center, and chiral center means what? The carbon atom attached to 4 different group is known as a chiral carbon. And as we know that chiral and the achiral means they are the optically inactive in nature. Chiral are optically active in nature. Always remember, chiral carbon atom or chiral molecule, chiral substrate are always optically active in nature. And now this carbocation is a highly stabilized due to this is a benzylic carbocation, and therefore, or we can call it as allylic type of the carbocation. It is normally well stabilized due to the resonance, therefore it is highly stable. Now there is a attack of nucleophile here. Now when the attack of nucleophile occur here, OH minus, attack of nucleophile from front side as well as back side. Suppose here is a front side attack, and here suppose is a back side attack on this, or back side attack. This is a front side attack. What do you get when nucleophile attacking from the back side? So what do you get here? Let me draw first. Here is a front side. Make the correction here slow, slightly different, so that we can clearly understood this one. This is a front side attack, because when this molecule is a planar in geometry, nucleophile approaches backside as well as from front side. If front side attack, here is a backside attack. If it attacking from the front side means this side, what do you get? Front side means whenever the leaving group is depart, that side is called as the front side, and opposite to that leaving group is known as a back side. When it is attacking from the front side, we are getting front side, suppose is here OH, one methyl group is here, one of the hydrogen atom we normally showing like this, and one of the phenyl group we can show here pH. This is one of the compound, and next one, let me here just remember as a clearly the space below is a slow, so let me draw here completely so that we can understood this one. This is a OH minus nucleophile attack, and nucleophile attack from front side as well as from back side attack. When it attacking from the front side, we are getting as a product like this, the methyl group which is over here, the hydrogen atom I am showing here, and one of the group phenyl group I am showing here. This is a chiral carbon, as we know that. And then if you put as a mirror over here, you can look it's that's why I am showing here. Now is when the nucleophile attacking from the backside OH is go there, then methyl group should be here, this one CH-3, not this. The methyl group should be shown by normal line, CH-3, hydrogen atom I am showing like this, and another one phenyl group I am showing by thick line, this is a pH. Now look at, this is a chiral carbon, this is also as a chiral carbon. What do you see? If you observe this reaction carefully, what do you see over here? Look at here, the name of this compound is a what type of, whether it is a R or S configuration. Look at here, 1, 2 and 3, 1, 2, 2, 3, and here we are getting 25% here, 25% yes, one phenyl ethyl alcohol. Ethyl alcohol, we are getting here 1 phenyl ethyl alcohol. We are getting 1 phenyl ethyl alcohol. Here 25% yes, 1 phenyl ethyl alcohol. Now here is a, what is this? This is a 75% R. This is a, sorry, here is a R, and here we are getting 1, 2 and 3. 1, 2, 2, 3. That is a yes, 1 phenyl ethyl alcohol. 1 phenyl ethyl alcohol, and this product, the starting compound is R. Here product also has a R. Therefore this type of the thing is called as a retention configuration we are getting. And this one, look at, starting compound is a R, the final product is a S. This type of the thing is called as inversion, right? One we are getting as a R configuration and the S configuration, and they are enantiomers of each other. One is rotating to the right hand side, one is rotating to the anti-clockwise manner. The rotations are different, optical rotations are different, therefore they are enantiomers of each other. This is a mirror we are putting here, and they are enantiomers of each other. 75 minus 25 you will get as a 50% of racimization. That clearly shows that in SN1 reaction there is a racimization. Racimization means what? Equal proportion of this two are getting, but 100% racimization is not possible in this case. So this is all about the stereochemistry of this SN1 reaction, that we are getting as a always as a racimization, R configuration as well as, but still here the 75% inversion product is always greater than the retention product. The 25% of the retention product cancel the inversion. So finally we are getting as a 50% of racimization for the SN1 reaction. So this stereochemistry or this stability of this carbocation depend upon the two factors. Number one, stability of carbocation. Number one is the stability of carbocation. Number one, stability of the carbocation. As the stability of the carbocation goes on increasing, the percentage of racimization goes on increasing. That you have to remember. And now suppose the stability of the carbocation goes on decreasing, the percentage of inversion product goes on increasing. So that is about the stability of the carbocation. Now second one, the nucleophilicity of the solvent, because for the formation of the carbocation, nucleophilicity playing as an important role for formation of the carbocation, because without solvent there will be no formation of the carbocation. And therefore let us see the nucleophilicity of the solvent, how it plays here. In this case, the nucleophilicity of the solvent that we are going to see over here, because first point we have seen here, stability of the carbocation. Second one, we are going to learn the nucleophilicity of the solvent. The nucleophilicity of the solvent. Nucleophilicity of the solvent, as we know that polarity goes on increasing, the stability of that carbocation also goes on increasing. Let us see one general reaction here. I am trying to explain this. R Br, RBr, it is a starting compound, or you can say it is a stage. When solvent is added over there, here as we know that it is a alkyl halide, bromine halide atoms are more electronegative in nature, and therefore they push the electron density toward themselves, and therefore bromine gets partial negative charge, whereas the carbon atom, which is electron deficient in nature, gets the plus delta charge over here. So this type of the polarization occur in stage number 1. Now when we are adding as a solvent, there is a breaking of bond between carbon and the halide atom. So let us see here, R dash 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 Br. Now here positive charge and negative charge, the solvent around these anions get surrounded. This is known as a intimate ion pair. This is a B stage. B stage is known as a intimate ion pair. Intimate ion pair. So this is a stage number B. We are getting intimate ion pair, means the water molecule gets surrounded around that, and the bond between carbon and the halide group is weakened, or it is breaking. Now after that, this is a solvent. Normally we are using here solvent. So this is a solvent surrounded here, solvent. And now what is happening here? There is a bridge is a form between these two anions. Here R plus and here is a Br minus. Now there is a wall between these two. They get what the solvent or separated solvent ion pair, solvated ion pair, separated solvent ion pair. Look at there, these two ions get separated from each other. Now this stage is known as a C stage. First one is a stage, B stage, C stage, and finally we will get as another R plus, then plus Br minus. So now look at in the these stages you can call as a D stage. Here this is a completely solvated, completely solvated ion pair. Completely solvent solvated ion pair, that is a D stage. These are the changes occur during this thing. When let us observe here carefully. Now RBr, as we know, it is a polar molecule, and polar molecule, this R gets plus delta charge, bromine atom gets minus delta charge. When the solvent is added, solvent gets surrounded around this, and therefore the bond between carbon and the halide is weakened. So that is shown by the dotted line. And this type of the intimate ion pair, still in this case the leaving group is not totally gone away from this, it remains in the close vicinity, and therefore in such intimate ion pair, this type of the situation they show as SN2, or they favor the SN2 reaction only. Now here look at here, separated solvated ion pair. Now R and Br, they get separated, no doubt about it, but that Br minus is not completely gone away from here, it remains in the close vicinity, and therefore the percentage of inversion product still here is greater. And now look at here, this R plus and Br gone away from that R, and therefore the nucleophile, when that R plus carbocation is a planar in geometry, nucleophile can attack from front side as well as from back side, and therefore in such cases there is a racimization product we are going to get. And this is all about the stereochemistry of the SN1 reaction. So stability of the carbocation and these things, the stability of carbocation depend upon, there are the different type of the